Hi all, welcome to part 10 of the video lecture on registers. So we saw many different categories of register. Started with the different capability, right? How we can feed input and output, serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. And the bidirectional register, the movement of the shift register, whether it can shift information towards right or left. And finally in part 9 we saw something called the universal shift register, which can do all those things in a single register, right? With the help of the control line, right? Hope it is clear. Now let's see something interesting. Anyways, this not given directly in your syllabus, but I am taking it because it's a very nice and interesting concept, and it finds many application. And for GATE exam and all those who are preparing, questions are mostly coming from this area. But anyway, I didn't see this topics explicitly mentioned in your syllabus. As part of register concept, I am taking it anyway. So those who are interested can watch, others can leave it. Okay, but it's very interesting thing. So let's see that. Linear feedback shift register. So it's nothing but the normal shift register only. Hope you remember how that shift register is constructed. That is with the help of D flip-flop. So 4-bit shift register is what is shown here, which is having 4 flip-flop, right? 4 D flip-flop, and its output of the first flip-flop is connected as input to the second one. The second one is output connected and is input to third one, like that. And okay, so that about it. The normal shift right configuration is what we are having. But what is different from the just shift register? Here we have a feedback path, right? So we have a linear feedback path, so that's why we call it as a linear feedback shift register. And the feedback path is, we can simply connect the feedback path, that is also there. Some variations are there popular with that concept, but anyway, what kind of combination we are seeing is the feedback we are taking with the help of some XOR gate. So we are having an XOR gate, and to that XOR gate, here the output like a Q1 and Q4 are taken as input, and it's so what is your D1? D1 is nothing but Q1 XOR Q4. But you don't have to do it always. What we need is just the XOR of some of the output should be given as input to the first flip-flop. So that kind of a configuration is what we need, right? And that you can achieve. So here as an example, shift linear feedback shift register we are taken like that. So okay, but you can think of a different one also, and you can try it out. So it is basically a serial in, serial out right shift register only, the first very fundamental one, the first one we studied. Okay, and where the serial input is generated as a linear combination of some of the flip-flop output. Some of the flip-flop output you take and produce a linear combination by doing that XOR operation, and that is given as input to some of the flip-flops. So here we just take an output Q1 and Q2, and that is that we passed through an XOR gate, its output we given for D1. But you can take any of these inputs, and you can do this XOR, and you can give us input to any of this register, and you can try it out. So we will see this as an example, okay, how it is working. So this is a very wonderful. So hope you remember. Let me ask you, what is your, as per this diagram, tell me what is your D1. D1, actually, you know, at any point this output Qn is nothing but the corresponding D, right? What is that D on that point? So this is the fundamental equation of any D flip-flop. So accordingly, tell me what is your Q1. So your Q1 is actually this D1, right? So Q1 is equal to D1. And now tell me what is your D1. And D1 is nothing but, you can see that Q1 XOR Q4, right? I am taking this Q1 here and Q4 here, and I am performing the XOR operation, right? So this Q1 is coming here, Q4 is coming here, and this Q1 XOR Q4 is what I am giving as D1, and that D1 is my Q1 after applying a clock pulse. Now what about my Q2? Q2 is actually D2, and what is D2? D2 is Q1. Fine. So this Q1 will be coming here, and that will be coming as Q2. Similarly, Q3 is your D3, and that is nothing but Q2. And Q4 is nothing but your D4, and that is nothing but your Q3. So this is something fundamentally we are having. So keep this in mind. So this is important, this observation, and accordingly we are going to see the state diagram, or the different states or different combinations of the output produced by this circuit. Okay, let me take a blank page. Okay, let's see that. So we are just observing our output, that is q1, q2, q3 and q4. Okay, and we need an initial value for that, because there is no way to input something to the circuit. It is simply doing this right shift and some kind of rotation, right? Just keep on doing. And okay, what about the output we can take like this, because all those things are available at any time, right? So assume that we are taking the output like q1 from here, and from here say q2, and from here say q3, and we are observing this q1, q2, q3 and q4 and what it is. Okay, we are taking the output like this. Now what about the input? We don't know, right? So we will assume some initial value of the input. And the thing is that you can assume 0 as the initial value, but if you are assuming 0, you will not get any new state. Okay, I will tell you that. So other than 0, assume any other value. So that is what we are going to do. Let's assume some random initial value. So what I am going to assume is something like say 1, 0, 0, 0. Some anything random you can assume. So assume random initial value. Okay, random initial value, and observe what is happening in the circuit, and you will see very nice property. So this is your random initial value. You can start with some other seed, so we typically call it a seed and all, and we will see that. Okay, now tell me, after applying the next clock cycle, the very next clock cycle, and you know from the figure it's clear that it is a positive edge triggered flip-flop, D flip-flop we are having, right? So this particular notation, positive edge trigger, and during the positive transition of the clock edge, you know the flip-flop will trigger, right? And you will get the next set of output. And you can see, so what you understood from the previous diagram is your q1 is nothing but q1 XOR q4. Hope you remember, right? This q1 is nothing but q1 and q4 XOR, and q2 is nothing but q1, and q3 is nothing but q2, and q4 is nothing but q3. So like that it is working. Yeah, now tell me, after this clock cycle, what will be your q1? Q1 will be q1 XOR q4. Tell me, q1 is 1 and q4 is 0. So 1 XOR 0, it is 1. Okay. And what is your q2? Q2 is nothing but your q1. So just to copy q1 like this. So your q1 is coming here as q2. Similarly, your q3 is nothing but q2, right? Q2. So the previous q2 will come here. Similarly, q4 is nothing but q3, this 0. And the only changes for q1, that is XOR of this q1 is actually q1 is equal to q1 and q4 XOR. Okay, that you know. Yeah, so that about it. Now again, after the next clock cycle, tell me the output. Now it is very easy for you, right? Simply you copy this q1 here, this q2 here, and this q3 here. Okay, and what will be your new q1? New q1 will be the previous q1 and q4 XOR. So this is the output. Now during the next clock cycle, again what you can do, you can copy them 1, 1, 1. So I'm just copying like this. Hope you understand the way how I am writing. Okay, then this q1 and q0 I am XORing, and I am writing here. Okay, if that is the case, I am not writing the clock. This will continue. Okay, so tell me the next output. It is what? 0, 1, 1 will come here. 0, 1 XOR, it is 1. Then 1, 0, 1 will come like this. 1 and 1 XOR is 0. Then that 0, 1, 0 will come here, right? 0, 1 XOR is 1. Then 1, 0, 1 will come here. 0, 1 XOR is 1. Then 1, 1, 0 will come here. 1, 1 XOR is 0. Then 0, 1, 1 will come here. 0, 0 XOR is 0. Then 0, 0, 1. Yeah. And 0, 1 XOR is 1. Then 1, 0, 0. And 1, 1 XOR is 0. Then 0, 1, 0. 0, 0 XOR is 0. Yeah. 0, 0, 1. 0, 1. 0, 0 XOR is 0. And then what is it? 0, 0, 0. and 0 1 XOR is 1. So it is going through this many states, and why I am stopping at this point, hope you understood, right? So this is we gone back to the starting stage. So our starting stage was like 1. So this is our initialization value, right? So this one, and we rotated, so we did something, and finally we are reaching back that. Now if you are repeating again, the same set of sequence will repeat. So that is clear to you, right? So this is where you can stop. So what we saw here is something like this. Let me draw in the next one. So as a state diagram, or shall I draw here? Otherwise let me try. Okay, so what we saw is initially it started with we started with 1 0 0. Okay, and then we moved to what? 1 0 0. Then we moved to 1 1 0 0. Then we moved to 1 1 1 0. Okay, then we moved to what? 0 1 1 1. Then we moved to 1 0 1 1. Then we moved to 0 1 0 1. Then we moved to 0 1 0 1 1 0 1 0. I don't know whether I am making a mistake. Okay, finally we will understand whether it is correct or not. 1 1 0 1, and then we will move to 1 1 0 1, then 0 1 1 0 0 0 1 1 0 0 1 1 1 0 0 1 0 1 0 0 0 0 1 0 0 0 0 1. Yeah, last one is what? Last one is the initial state. So what I can do is I can connect this back to this. So what I was trying to say is this is a state diagram, right? The corresponding state diagram is what is shown here. State diagram. And can you observe this? So if you are looking at the corresponding decimal value, see, you can see that these binary combinations are unique. They are not repeating at any point. So this is your what is this? This is your 8, right? This is your 8. Then 1 1 0 0 is 12. Then this is your 14, 7, 11, 5, 10, 13, 6, 3, 9, 4, 2, 1. Yes, and you can see that from 1 to 15 you can see all the numbers. Which is missing? 15 is missing, right? 1 second. As expected, I made some mistakes. So what I done is the diagram I corrected completely. I mean the state transition and all. In between here I made a mistake. Like after this, instead of writing this 15, I written something different. So that is why some sequences change, replace, compare with the previous one. Or you just write in your own way, so that you will not make mistake. Okay. So this is the final one. This is the corrected one. And you can see that you can here if you are looking at the state number 1 is there, 2, 3, 4, right? 5 is here, 6, then 7, 8, 9, 10, 11, 12, right? You can see that 13, 14, 15, like that. From 1 to 1, 1 to 15, there are 15 unique states given by it. So this is a very important concept that we are using in computer science. So you might heard about something called random number generation. Okay, and you know this, we can't predict the pattern. So it depends on what is our initial value. As we started with the initial value 8, we got the pattern like 8, 12, 14, 15, like that. If you're initializing with some other value, we will be getting a different pattern. So that initial value typically we call as the seed of the random number generators, right? So this is the seed of the random number generator. So this will act like a random number generator. so we typically use the word pseudo random number generator circuit. Okay, so that is the speciality of it. You initialize with any value, accordingly some random sequence of numbers will be generated, and it is unique and it will contain everything from 1 to 15. So what is that 15? 15 is actually 2 power 4 minus 1, right? So in general, so here what I am having is something like 4 flip flops. So using 4 flip flop or use which act like a 4-bit register, right? 4-bit register. 4-bit what kind of a register? Linear feedback shift register, right? 4-bit linear feedback shift register. Linear feedback shift register. Okay, 4-bit linear feedback shift register. It is capable of generating can generate random numbers from not 0 is an exceptional case, we will see that, from 1 to 15. So in general, what you can conclude, you can try with the 4 flip flop, 5 flip flop and all, and you will see that using n such flip flops, what kind of flip flop? D flip flop, connected as some linear feedback shift register, it can be anything. Okay, that XOR and all, you can connect output of any two of them, accordingly some random different random sequence you will get. Okay, so it can generate pseudo random numbers from 1 to 2 raised to n minus 1. So that here it is 4, 2 raised to 4 minus 1, like that. In general it will go from 1 to 2 power n minus 1. So what is the problem with the 0 0 0? So that is the question. So if I am initializing it with the 0 0 0, you will see that. So that is the first advice, don't initialize with the 0 0. So if you are initializing with the 0 0 0, if this is the current state, what is the next state? So that what is your Q1? Q1 XOR Q4, 0 XOR 0 is 0. Then other bits are just shifted. So next state is also the same, right? So you are not getting something different. What you need is, your purpose is to get random numbers, right? So it will not give you that. So it will look like that. We don't want it. We just want some different set of numbers. Okay, so that is our requirement. So the advice is like, don't initialize with the 0, with the all zeros. So that will not work. You can start with any other value, it will work nicely and it will perform like a pseudo random number generator, and that finds many application in computer science. Okay, so that about it. Hope you get a very idea about, and whatever be the specification they are giving in your exam, now you are capable of constructing a register for that. Okay, so keep everything in mind. Next we will explore something called a counter circuit. Okay, so thanks for watching, and doubts if any, you can ask, you can approach me at any time. Okay, thank you.